In example number 1, an important example of an infinite series is the geometric series. We would have a plus a times r plus a times r squared plus a times r cubed plus the nth term, which is a times r times n minus 1, plus as we continue. So therefore, we would have the summation of n is equal to 1 to infinity of a times r to the n minus 1, where a does not equal 0. Now, each term is obtained from the preceding one by multiplying it by the common ratio r. And we have already considered the special case where a is equal to 1/2 and r is equal to 1/2. Now, in step number 1, if we let r equal 1, then the sequence s subscript n is going to equal a plus all the way to a, which would equal n times a, which would be approaching positive or negative infinity. Now, since the limit as n approaches infinity of that sequence doesn't exist, then the geometric series diverges in this case. Now, if we let r not equal to 1, then we would get the following sequence. We would have a plus a times r plus a times r squared all the way to the nth term, which is a times r times n minus 1, and r times s subscript n, which would equal a times r plus ar squared plus ar n minus 1 plus ar to the n. So what we're going to do is we're going to subtract these two. So we have s sub n minus r times s sub n, which is going to equal a minus a times r to the nth power. So the first thing we can do on both sides is factor. So we can factor out s subscript n and factor out the a. And then solving for s subscript n, we're going to divide both sides by 1 minus r. So that's going to give us our third definition. S subscript n is going to equal a times 1 minus r to the n divided by 1 minus r. So a way to look at this is by looking at figure 1. It provides a geometric demonstration of the result in example 1. If the triangles are constructed as shown and S is the sum of the series, then by similar triangles we can see that S is proportion to A is equal to A is to A minus AR. So then we would get S, which is equal to A over 1 minus R. Now, if r is in between -1 and 1, and we know from 8.1.7 that r to the nth power approaches 0 as n approaches infinity, so now we can take the limit of this sequence as n approaches infinity. So we're going to take the limit as n approaches infinity of a times 1 minus r to the n divided by 1 minus r, and then we can distribute the a to the numerator. So we get the limit as n approaches infinity of a minus ar to the n divided by 1 minus r. And then what we can do is we can then reorder this. We can say that this is the same thing. So they both have a common denominator. They have a common denominator of a 1 minus r. So the first one we have a divided by 1 minus r minus we have a times 1 minus r times r to the nth. So all we did was separate these using fractions, and you're subtracting them. So now we can take the limit of both of those since it's a subtraction. So we can say the limit as n approaches infinity of a divided by 1 minus r minus the limit as n approaches infinity of a divided by 1 minus r times r to the n. Now a over 1 minus r is a constant, so we can factor that out. So when we take the limit of the first one, we get the constant a over 1 minus r minus we have the constant a divided by 1 minus r, but the limit as n approaches infinity of r to the nth power is 0. So 0 times that constant just leaves us with a divided by 1 minus r. Thus, when the absolute value of r is less than 1, the geometric series is convergent, and its sum is a divided by 1 minus r. If r is less than or equal to -1, or r is greater than 1, then the sequence r to the nth power is divergent by 8.1.7. And so by equation 3, the limit as n approaches infinity of that sequence does not exist. Therefore, the geometric series diverges in those cases. And so we're going to summarize the results of example 1. The geometric series of AR to the n minus 1 as n is equal to 1 to infinity is convergent if the absolute value of r is less than 1. And its sum is equal to a divided by 1 minus r, where the absolute value of r is less than 1. And if the absolute value of r is greater than or equal to 1, then the geometric series is convergent. So in words, we can say that the sum of a convergent geometric series is taking the first term, dividing it by 1 minus the common ratio.